Okay, and I want attention up here. Let's have a look. So if we're going to work backwards on this, let's think about a couple things we could do here to turn our thinking around on this, right? So if we were given the function, remember we wanted to figure out end behavior, we wanted to figure out where the x-intercepts were, and then we wanted to kind of chart the function's behavior between those. This is easier. This is easier. They're telling us some important things about this. They're telling us, first of all, that this is going to be a cubic function. So let's take a second and just talk about, what that word means. If it's a polynomial and it's cubic, what's that mean? Okay, good. So the degree of the polynomial, the biggest power of x, is 3, like a cubic function. Okay. What if it were a quartic polynomial? What's going to be the degree? 4. What if it was quintic? 5. What if it was quadratic? No.
8.
No. What's the quadratic we've dealt with? 2. Yeah, it's 2. Good. That's going to be like an x squared one, right? It's going to make a polynomial, or excuse me, a parabola, right? Okay, so it's cubic. So they're telling us that the degree is going to be 3. So it's odd, isn't it? Okay. There's 2 important pieces of information here. Let's think about for a second. Let's review. We looked at a whole bunch of different power functions the other day. X squared, x cubed, x to the 4th, x to the 5th, x to the 6th. We found some patterns. The even functions, right, where we had even polynomials, where the degree of the polynomial was even, what was the end behavior like? What did it do? Like for x squared, x to the 4th, x to the 6th. Yeah, on both sides, right? It did this, right? That was the end behavior of an even function. Okay, so what if we had an even function and the graph went like this instead? What's that tell you? How do we get from here to here with an even function? What do we have to do? Yeah, we got to multiply by a negative. A's got to be negative, doesn't it? Right? The number out front, and look what it says here. The factor out front, a. In this case, we're going to make it really simple. It's either going to be 1 or -1. That's it, right? So if it's 1, we don't write anything. 1 times something is just that thing, right? We never write the 1. If it's -1, we would just put a negative sign out in front, right? That's for an even function. What's normal in behavior for an odd function, like x cubed, x to the 5th, x to the 1? What's that look like? Even was this. What's odd?
One side goes up.
And which side goes up?
The
The right side goes up, so it's like this, right? That's normal odd behavior, but what if it does that? What's that going to be? Negative? That's going to be negative odd behavior. But we got to multiply the function by -1 to reflect it over the x-axis so it goes from here up to there, right? So which one is this? Positive or negative? Positive, yeah. So we know, so right away, we know that a is equal to +1, okay? Based on the end behavior, right? That's half of the problem, really. Now, the rest of it, we just have to come up with the factors that we multiply together to get this. Where do they come from? Where are we going to get those? Like if we were to, here, I'm going to go back just a little bit. For just a second, let's go back to one of these. It's not doing that. There it goes. Okay, so look at this guy. This is a harder one, right? This is one where they give us the function, and we've got to make the sketch. What are the x-intercepts of that function? 6, 3, 1, and -2. Everybody agree? And we get those by setting the function equal to 0 and solving using the zero product property, right? The 0 of that factor is 6, the 0 of that factor is 3, 0 of that factor is 1, and that factor gives us a 0 of -2, right? Okay, hold that thought. Now, what if we go back to this problem? There we go. So now we're going back to this problem, right? We're working backwards. This time, they're giving us the x-intercepts, not the factors. But the x-intercepts were related to the factors, weren't they? What's going to be Tyler, what's going to be the x-intercept, or the factor that goes with an x-intercept of -1, do you think?
1.
Well, by 1 you mean x plus 1, right?
Yeah.
Okay, so the factor that goes with that guy is going to be x plus 1, because if I set that equal to 0, -1 makes that 0, right? Okay, Bailey, what's going to be the factor that goes with the x-intercept x equals 2? X minus 2, right? It's got to have an x in it, right? But does that make sense? Because the 0, when x is 2, that would be 0, right? And sir, what's going to be the factor that goes with the x-intercept 4? X minus 4. And we already said that the number out front is a 1, so we don't even write it. Okay, and so this is our answer. Right there. Okay, make sense? That's the function that goes with that one. Okay, let's try another one. Okay, what about this guy? It's cubic. So first of all, let's look at the end behavior. Is it positive or negative end behavior? It's negative, isn't it? Because it's going up on the left and down on the right, and that's opposite, right? So we know right away that A is equal to -1. Okay, but what about the x-intercepts? Something's different here. What's going to be the factor that goes with the x-intercept -2? X plus 2. Okay, so we get, what about this one? So x plus 0 or x minus 0, just x, right? But if I do that, it doesn't quite work. It doesn't work because is that going to make a cubic polynomial? I'm only going to get an x squared out of it. So something is wrong here. But there are only 2 x-intercepts. So how many factors does we need to have? 2, right? We only get 1 x-intercept for each distinct factor. But what could be going on here?
Negative sign.
The negative sign out front, we need that too. So I'm just going to put a negative out there. True. But something's still not right here. Something's still not working with this. Let's go back again. Let's go back to an earlier problem for just a second. Let's go back to one like, how about this guy? Okay, no, not that one. That's not what I want. I want one like this. Yeah, like that. Okay, what are the x-intercepts of that one? So you're going to get, what are they again? What are the x-intercepts? X equals 5 and -4. And it is cubic, right? We can see that it is, I mean, it is going to be cubic. And so we don't know if this is the right answer, but we know we've got to have x-intercepts at -5 and 4. But what did we decide happened if that factor was being squared? It did something different, right? Remember that when factors were not squared, they always corresponded to x-intercepts where the function cut right through the x-axis, right? Everybody with me? Okay, but what happens if the factor is being squared? That changes things. It grazes it and bounces, right? So the function would have to bounce off the x-axis at -4, right? Remember talking about that? Like, I don't know, what was that? Tuesday? Okay, so now let's go forward and let's look at this question again. Come on. Okay, so yeah, we've only got 2 x-intercepts, but one of them's being squared, right? Which one's being squared? Yeah, that one is, right? Because look, it's bouncing. This one is bouncing, it's bouncing off of the x-axis like a parabola. It's not cutting through it. So this is the one right here that's actually going to correspond to, I don't need to put the parentheses around it. it's going to be x squared. Because of that behavior, it's going to be squared. This first one over here cuts right through, so that one we'd expect to just be x plus 2. And then out front, we said it's going to be negative. So that's what our answer should look like this time. Okay? And does it matter if the x squared goes first or the x plus 2? Makes no difference, right? But what is important is that it's the x that's being squared, not the x plus 2, right? Okay, let's try one more of those. Make sure we got this all figured out. What about that? So it's quartic, and it's even, right? Because both the end behavior, the ends both do the same thing. Positive or negative end behavior? Negative, it's going down instead of up. So one thing we know right away, is that. Okay, what are my x-intercepts going to be? I know I'm going to get a negative out front. What's that one going to be? So x plus 7. What's that one going to be? X plus 1, good. And then how about this guy? X minus 6, but what's unique about that one? Yeah, it's bouncing. It's not cutting through, it's grazing it. So it's going to be x minus 6 squared. Okay, make sense? All right, good. Okay, so that's that assignment. Now, how about okay, there's some questions that come up here. Where they ask us for a bunch of, 3. This is a really short assignment. So for 3 polynomials, they ask us exactly how many x-intercepts does it have. And then in general, a polynomial of this degree could have at most how many turning points. So let's just do a quick exploration of this, and let's see what we find. Let's take a cubic function, for example. Cubic function could have at most how many x-intercepts? You guys know this. How many factors could be in a cubic? 3. We could have 3, right? But that's the most we could have is 3, right? 3 factors involving x's, because then that would give me x times x times x is x cubed. So what's that going to look like? Well, if it's got 3 distinct factors, then it's going to do something like that, isn't it? Right? And so I'm going to get my 3 x-intercepts. Could I get less than 3 x-intercepts? I could, right? I could. What if I took this function and I just moved it up? Or, easier yet, how about if I just, move this line down? Like that. If it were like that instead, wouldn't that be a situation where I'd have 2 x-intercepts? Right? And if I move it even further, down like this, I get 1, right? Could I ever get 0?
Yeah.
How could I get 0?
You just move the line
Down farther, but okay, what's going on, Mallory? Still goes down. That arrow means it goes down forever, right? Think about the end behavior of an odd function. Like in this case, it's positive end behavior. It goes up forever this way and down forever that way. So there is no way it could ever not pass through the x-axis at least once. Agreed?
Agreed.
Okay, so I'm stuck with at least 1, but the most I could get is 3. Okay, what about turning points? No matter what, no matter where I put this thing, this guy's got 3, has how many turning points? 2. Could I get less than that? There is one way I could get less than that. I could graph a function that goes up, maybe it does something like this, like just plain old x cubed, where it's got no turning points, right? Does that make sense? but the most I could get is 2, right? Let's look for a pattern. So we said that a cubic function, so if the degree is 3, it could have at most 3 x-intercepts, 1 for each factor, right? And it could have at most 2 turning points. And by turning point, we mean either a maximum or a minimum, where the function turns around its behavior, right? Let's look at an even function. Let's look at a quartic real quick. So if we take something like a quartic has x to the 4th, so I could have, at most I could have how many x-intercepts? 4. Right, so it could go like this. Something like that. Right, I've got 1, 2, 3, 4. Could I get 3 in some way?
Yeah.
I could. That would be 3, wouldn't it?
Yeah.
Could I get 2?
Yeah.
Yeah. Could I get 1? Right there. Could I get 0?
Yeah.
I could this time, couldn't I? Could get 0. But the most I could get is 4. Okay. What's the most, now this is the most active, busiest quartic function I could get. And how many turning points are there? 3. I could have fewer than that if I didn't have, maybe it doesn't have, maybe it just goes up and only goes down once, for example, right? It's possible. But the most it could have apparently is 3. What's the trend here? If I took a polynomial with degree 11, what's going to be the most x-intercepts it could have if it has degree 11? 11. What's the most turning points it could have? 10. How'd you get it? What was our pattern? 1 less. And it has to be 1 less, doesn't it? Because look at the picture. The turning points can only happen, between x-intercepts, right? I mean, maybe if I move this line, they could be outside of that. But the point is, if I have the largest number of x-intercepts, the turning points can only happen in between those. And so if they have to happen in between, that means I'm going to have 1 less turning point, right? Because they have to be bracketed by the x-intercepts. All right, so that's kind of a lot of stuff. But what about this then? So exactly how many x-intercepts does that function have? It's got 3. How come? It's got 3 distinct factors, x minus 10, x minus 6, and x minus 2. So it has 3 x-intercepts. A polynomial of this degree could have at most how many turning points? 2, right? Okay, how about that? Let's go one more. How about that guy? How many x-intercepts does it have? 2. What degree is that polynomial going to be? How am I going to know? Okay, let's get everybody focused up here, please. So how am I going to know? Now think about this. If I were to multiply that whole thing out, what would the biggest power of x be? And we're going to do this. This is what we're doing starting Monday. I'm going to start talking about adding and subtracting and multiplying polynomials. And it's really not very hard stuff. If I were to do that, x plus 2 squared is just x plus 2 times x plus 2, right? If I multiplied that out, would everybody agree x squared is going to be the biggest power of x? And then if I multiply that whole mess by x plus 1, I'm going to multiply x times x squared is going to give me x cubed, right? So if I want to determine what the degree of a polynomial in factored form is, all I've got to do is look for each factor. I'm just going to look at whatever the power of x is in there times whatever power that factor is taken to. So this is x to the 1 times 1 is 1. This is x to the 1 times 2 is 2. And 1 plus 2 is 3. Right? Does that make sense? So this is going to be cubic. And so the most it could have is 2 turning points. Right? Try one more of those. You try. So let's try, how about this guy? Oh, never mind. Okay, never mind. I think you got that. Here's the last thing I wanted to end with, and this is a pretty cool problem. This is something I want you to get some exposure to this. Remember I talked to you the other day about how if you want to make just ridiculous amounts of money, you just have to be really good at calculus, and then go to Wall Street and they'll pay you all kinds of money. Okay, true story. But why? What does calculus do? It just so happens that this is the exact kind of stuff we're talking about in my calculus class right now. This is interesting. Math really, in a way, I mean, I think all math can be interesting, and they're interesting relationships, but to me, really, calculus is where it gets to be very interesting. Calculus is where in a sense, all you do prior to calculus is get ready for calculus. And then when you get to calculus, you can actually do some important stuff. Calculus allows us, among other things, to do problems like this where we want to optimize a quantity. When you optimize something, what's that mean? What's it mean to optimize something?
Make it better.
Make it better. In fact, make it the best it can be, right? So if we've got some, what's an example where you could do this? Like if you were going to, let's say you're setting up a sprinkler, and you want the sprinkler to reach as far out in the grass as it can go, and you can control maybe the angle at which it's shooting the water out. You could sit there and just kind of tweak that thing and see what angle is going to give it the furthest reach, right? By doing that, you'd be optimizing the area of the sprinkler. Okay? You're going to make something, you're going to tweak something to make it perform its very best. Well, this is what calculus, one thing it's really good for. It allows us to, like on Wall Street, we'd be maximizing profit. We want to tweak all the things we can control so that we can maximize the amount of money that we're making. This is something a little different here. This is, we've got a sheet of cardboard and we're going to build boxes. Let's pretend that we're doing a fundraiser and we're going to sell Algebra 2 brand blueberries. And so we're going to sell these, we're going to make a profit, but we have to, if it's like a real business, we'd have to look at all our expenses also, right? So profit is going to be the amount of money coming in minus how much money we spend, our costs, right? It's going to cost us some money. We got to go get the blueberries or buy the blueberries wholesale. We've got to put them in boxes, right? And so we're going to have some expenses to build the boxes, and that's what we're going to look at here. How could we minimize the amount of money we're spending on boxes? Well, in order to spend as little as possible, what do I probably want to maximize for each box? We're going to put the blueberries into the boxes. Volume, right? We're going to maximize the volume. And so look what we're starting with. We're starting with boxes. We're building them out of 31 by 28 centimeter rectangular sheets of cardboard. Okay. How are we going to build the boxes? Well, we're just going to do this. We're going to take this 31 by 28 sheet of cardboard, and we're going to cut along the red lines and fold along the blue lines, right? So does that make sense? If I were to cut, essentially I'm cutting these corners out and just getting rid of them. And then I'm going to fold these flaps up along the blue lines. Does everybody see that when I do that, I'm going to create a box? Right? It's going to be an open box. There's no top on it, but that's all right. We're just going to sell the blueberries in these open boxes. So there we go. Okay. So there's our picture, right? Now I've got very limited artistic ability here, but would you agree that this is essentially what our boxes would look like? Something like that? Everybody agree? Okay, that's when we make the red cuts, remove the corners and fold the flaps up. We'll just tape around the corners maybe, so it'll stay a box. Okay, good. So what's going to be, how are we going to make our cuts? How far up the cardboard do we cut to make to cut out the square corners? We don't know, right? That's what we're trying to find out. Where do we make our cuts so we could maximize the volume of the box? The size of the cardboard is already given to us. It's 31 by 28, but where we make the cuts is unknown, right? That's the unknown that we're trying to solve for, isn't it? So that must be a variable. We don't know what the answer is yet, so let's call it x. We're just going to move x centimeters away from the corners to make our square cuts. Everybody agree? So if we do that then, what are the dimensions of this box going to be? We don't know what x is yet, but which dimension in our box would end up being x? The height, wouldn't it? Isn't x going to be, by moving up a distance x, that's also going to be the length of our cuts, isn't it? Right? So if that distance is x, doesn't that on our picture just become the height of the box when the flaps are folded up? Right? Casey, can you tell me, this is tricky, can you tell me what the length of our folded box is going to be? The cardboard started off being 31 centimeters, right? But then we're folding up these flaps. So what's the not the width or the length of the cardboard, but the length of just our folded box going to be? Say it again. Say it louder. Not sure? Yeah, Maisie, you got an idea? It's not. Is it less than 31? It is, isn't it? Because we folded up the flaps. How much less than 31? Well, we don't know for sure, right? Because we don't know what x is yet. So we're probably going to have x's in our answer. Minus 2x. Yeah. We start off with 31, and when we fold up the flaps on the ends, that means we're going to be subtracting x from the overall length twice, right? One for each end. Everybody see that? So we end up here with 31 minus 2x is the length of the base of the box, isn't it? Okay, what do you think, Alexis, what do you think about the width then? What's that going to be? Start off as 28. But we're going to fold those flaps up, same. It's going to be less than 28, right? If I fold this flap up right here, how much was 28? How much of that width am I losing if I fold that one up? Well, we don't know for sure because we don't know what x is, but it's going to be x, isn't it? Whatever x is, I'm going to lose that much and that much down there. So 28 what? Minus 2x. Yeah. So those are the dimensions of my box, aren't they? Right? So then how do we calculate the volume of a rectangular prism like this, going back to geometry? Don't I just multiply the dimensions? Length times width times height, right? So we end up with the volume. Now, it's going to only have x's in it, so I could write it as v of x. Volume as a function of x is just x times 31 minus 2x times 28 minus 2x. Okay, that's going to be a polynomial if I multiply it all out, isn't it? Right? I'm going to end up getting, and just remind ourselves, what does a polynomial look like? If I multiply that whole thing out, I'm going to get something like this. I'm going to get something of the form that's going to look similar to this, like 7x cubed minus 3x squared plus 12x minus 9. Something like that, right? Polynomial just means many terms. Remember what the rules were for each term. The coefficients had to be real numbers, right? Just couldn't have i's in them, right? Brandon, you remember what the rule for the exponents was? We had an x cubed, an x squared, an x to the 1. And what was the power of x here that we don't even write? It wouldn't be 1 because x to the 1 is x. X to what power would just be 1? The whole thing would be 1.
Oh.
Anything to what power is equal to 1?
1.
0. Yeah, so I could write it as x to the 0. Now, I wouldn't do that, right? I would never write it that way because there's no need. What good does that do, right? X to the 0 is just 1, but I write it that way one time. So we could just see that what are the exponents then? The smallest exponent would be 0. The next smallest would be 1, then 2, then 3, and we'd keep going if the polynomial were bigger. So what are the set of all those numbers? 0, 1, 2, 3, etc. Remember? What do we call that though? That set of the set 0, 1, 2, 3, etc. is the set of what? This is one that we talk about in math every once in a while. That's the whole numbers. 0 plus all the positive counting numbers, right? Okay, so that's all a polynomial is just real number coefficients times whole number exponents. Add them up and it's a polynomial. Okay, and we're going to have a lot more practice with that. For now, though, here's what we got, right? If I multiply that out, that's what I'm going to get. Let's see what it looks like. Let's just put it in Desmos and see what this function looks like. And this is where you kind of start to get a little more intuition about math, is when you can kind of start to put things like this into a mathematical function and compare it to the graph. Would you guys please put all your phones away? I would really appreciate that. Thanks. So, yeah. Let's go. Thanks. She's not here. Okay, here it is. Whoops, there it is. There's the function, right? X times 31 minus 2x times 28 minus 2x. That function doesn't look like much right there, does it? It just goes, well, I guess it's red, and it crosses the x-axis at 0, and again at 14, and then again like 15 point something. But it looks like it goes pretty high, doesn't it? Right? Let's maybe see if we can see how high this function goes. Well, it's going pretty high. Okay, it's going to go up. It looks like maybe the first part stops right there, right? The first peak stops, and then maybe it goes back up again. So less than 2,000, right? So I'm going to tweak this just a little bit. Let's look at this function in the interesting places. So if you want to, in Desmos, if you want to change the graph settings, you go up to the wrench. Those are the graph settings. And I can control along the x-axis, we're going to go from what bottom value. How about if we go from like -5 up to, I don't know, let's just say 20. Okay, now that starts to look a little more interesting, right? If we keep the y's on that really big scale. Okay, so if I look at just the polynomial by itself, I want you to see one other really important thing here. What's the domain of any polynomial? We talked about this the other day, right? Polynomials go from negative infinity up to positive infinity, right? There's no restrictions in the domain, mathematically, right? If I graph this function, would be graphed everywhere. Except this isn't just a math problem, right? This is a problem that's actually modeling the volume of our blueberry boxes, right? So not all values of x really make sense, right? Like maybe, I mean, it would make sense for us to say, okay, x could be 2. So we're going to move up 2 centimeters along the sides and make our square cut. That makes sense. That's going to give us some volume, isn't it? We're going to get a pretty shallow box. It's probably not the right answer for the best volume to maximize volume, but it's going to give us a box. What if I tell you to make the cut, let's let x equal -5. What's that look like? So I'm going to move up the box -5. That's like I'm making my cut down. Well, I'm not even cutting the box, right? That doesn't make any sense. In fact, no negative number is going to make any sense, is it? Right? Kind of the lower limit. I mean, I could make a microscopic cut. I could go up 1/100 of a centimeter. It's going to be probably a bad idea, but I could do it if I were precise enough. So really, any value bigger than 0 would be worth looking at, maybe, right? But then, would it make sense for me to make my cuts 1,000 centimeters from each corner? That doesn't work either, does it? If I start there and I go up 1,000 centimeters and over 1,000 centimeters, I'm not even cutting the cardboard, right? So what's the biggest value that x could have that would make any sense for us in terms of our actual geometric, box that we're creating here? I could make the cuts. I could go up, like if I went up 10 centimeters, I'm going to make pretty big cuts and end up having a pretty small base. But at what point does it not really work anymore? What do you think?
15.5.
Okay, so 15.5 would be half of 31, right? So if I made my cuts at half of 31, but that wouldn't make sense on the sides because I'd actually be overlapping in my cuts. So what about the 28's, the smaller dimension? Do you see that it really wouldn't work if I made my cuts down as far as 14? That's the furthest I could go, and then I wouldn't really have much left, would I? If I made my cuts, see what this would look like. If I went up 14, my cut's going to look kind of like that and kind of like that, right? Same thing over here. I'm going to go over 14 and up 14. Well, what's going to be left? All that stuff I'm just throwing away. My box is going to be a pretty crappy box. It's just going to have a fold, one fold in the middle, and I'm going to fold it up like, it's just going to look like this. It's not much of a box, right? But that would be kind of the other upper limit, wouldn't it? If I make my cuts more than 14, it doesn't even make any physical sense. So how does that look on our graph? The math gods are pretty smart. They know that by looking at this graph, look, they know that I'm going to get zeros at x equals 0, and I'm going to get 0 volume at x equals 14, right? I don't really need to look anywhere else. I'm only looking for values of x that are in between those, right? Well, what did I graph here? I graphed, lost my pen. Where did I set my pen down? What did I do?
It's right there in the book.
Oh, there it is. Thank you. Okay, so what's on this axis? Well, this is all just equal to v of x, isn't it? Right? So this is going to be the volume. My function is calculating volume, and x is telling me how far my cuts are going to be from the corner. Well, point on that graph up there and tell me where's the best place? It looks like it's roughly 5-ish, doesn't it? It's exactly, would you agree that it's exactly this point right there? If I touch the graph near the maximum, it's going to tell me what the exact maximum value is. So, yes?
Yeah, riddle.
Oh, okay. Well, does everybody see how we finish this stuff? So this tells us that the volume is going to be the biggest because that's the peak of the volume function, right? When x is 4.898, so about 4.9 centimeters, right? That gave us the biggest volume, right? Okay, so you're going to do some problems like that.
And you just show us how
I need to learn.
Oh, okay, I still haven't done all my classes. I'll do it on Monday. I'll finish my other classes up. Okay, here's your riddle.